Hello everyone, welcome to our differential equation class. In this video we continue our study on matrix algebra. We are going to start computing a formula for the inverse of a 2 by 2 matrix. Then we are going to use this formula and everything about matrix algebra we have seen in a previous video to solve equations where the unknown is actually a matrix. And then we end up with a little remark that the determinant of a matrix can be generalized from 2 by 2 matrices to 3 by 3 and n by n matrices. This formula for the determinant of a 3 by 3 matrix will be needed in a later video. So that's the plan for today. Let's start computing a formula for the inverse of a 2 by 2 matrix. So let's assume that we have a matrix A that is 2 by 2 and is invertible, and let's denote as usual the inverse by A inverse. So let's assume that we have a system of equations with that matrix as the coefficient matrix of the system. Then what we can do if the matrix is invertible is multiply by the inverse on both sides. And this is what we are going to get. And then we have the inverse here acting on the vector B. Well, on the left side we get that this product of the matrix by its inverse is the identity matrix. So actually we end up with an equation for the solution, and the solution is the inverse matrix acting on B. So this is a way to find a formula for the inverse matrix. You start with the most general 2 by 2 system of linear equations with an arbitrary right hand side, the coefficient matrix, an arbitrary coefficient matrix, and you write the solution of that system. X is going to be a vector, and then you write this solution as a matrix acting on the right hand side vector B. Then that matrix has to be the inverse matrix. So a little bit more precisely is we need to solve a system of equation of this form where A is an arbitrary coefficient matrix 2 by 2 and B is an arbitrary right hand side, and we need to write the solution in this way, because if we write the solution in this way, then this matrix that we have here is the inverse matrix of the coefficient matrix A in the system. So that's the plan. We are going to solve the system and find the formula for the inverse matrix. So let's solve that problem. Solution. So what we need to do is we need to write the solution for this system of equations. A acting on X equals some vector B. Let's write these equations in components. So we have a matrix A with components A, B, C, D, acting on a vector with variable vector with component x1 and x2, and the result has to be equal the given vector b1, b2. If we write this in the old way, by doing the matrix vector product that we have here, we get two equations, and the first equation is A acting on x multiplied by x1 plus B multiplied by x2 equal b1, and C multiplied by x1 plus D multiplied by x2 equal b2. So this is the system of equations written in the usual way, and now let's copy that over here to keep working. What we are going to do to solve this system, there are many ways to do it, isn't it? We compute from the first equation x1 and we plug that into the second equation and we solve for x2, and this is the substitution method. But we are going to do something slightly different, that involves less assumptions on the coefficients. And what we are going to do is we are going to multiply the first equation by the coefficient d, the second equation by the coefficient b, and we are going to subtract these two equations. That's what we are going to do. Why? Because if we multiply by d the whole equation, in particular this term, and by b this term, you see we are going to get the same terms. If we subtract the two equations, this is going to cancel out and we are going to be able to compute x1. So let's see that in a little bit more clear way. Recall, what we need to do is distribute the products, do the difference, and what do we get? We get d multiplying a times x1 from the first term plus d multiplying b times x2, and then we need minus these two products, so minus b multiplying c x1 minus b multiplying d x2, and this is equal, in the first side we have d times b1, and then minus b multiplied by b2. Alright, and now you see why we did this calculation, because this term, this term goes away with that term, and then we can pull common factor x1 on the other two terms, and what we get is d times a minus bc, let me write it down as ad minus bc is common factor of, here we have x1, and on the other side, well, what we had? D b1 minus b2. We did nothing there. So we are going to be able to solve for x1 if this quantity is different from 0. So we are going to give that quantity a name. We are going to introduce the quantity delta, that is, so this here we call it delta. It's just a name for this combination of coefficients ad minus bc, and we assume that delta is different from 0. So with all that, then we got our solution. x1 is going to be 1 over delta. That's why it has to be different from 0, of course, and then d b1 minus b2. And this is how we compute the first component in the solution, x1. How do we compute the second component? Well, in a very similar way. We start with the system of equations right here, but now instead of the multiplication we did above, we do multiplications so that x1 cancels out. That means we need to multiply by c the first equation and by a the second and subtract. So let's do it. Let's multiply by c the first equation, by a the second equation, and subtract. What do we get? Well, if we do that, we are going to get c times a x1 plus cb x2, and then from the second equation we are going to get minus ac x1 minus ad x2, and on the other side we have, from the first equation, we have c b1 minus a b2, and we see now that this term and that term go away, and we pull common factor from the other two terms, and we get something like cb minus ad multiplying x2. Let's make a little bit of space here, there, and then on the other side we get the same thing as before, c b1 minus a b2. Okay, but what we have here is the opposite of what we had over there. So this is minus delta. So what we have here is minus, okay, let's put here minus delta x2 equal c b1 minus a b2, and well, so we have assumed that delta is different from 0, so we can divide everything by negative delta, and we can distribute the sign of the negative sign on the other two terms, and we are going to get that x2 is equal 1 over positive delta, and now we put the negative sign inside, negative c multiplied by b1 and positive a multiplied by b2. And here is the solution for the second component. We solve our system. But recall, we don't only need to solve the system, we need to write it down, in this way. Matrix acting on the vector b. To do that, let's copy the solutions we obtain. Copy, let's put it here, paste, more or less over here, and then the other solution, copy, let's put it here, paste, just to have them both together. And now recall what we want to do. What we want to do is we want to write these solutions as a single vector, which is going to contain x1 and x2. Each of these components has a 1 over delta, so that is going to be common factor outside. Something like this. Well, something like that. Okay, so 1 over delta. And then what do we have in the components? Well, the components are going to be the b1 minus b2, and the other component is going to be minus c b1 plus a b2. But this clearly is a vector that depends on the vector b. Let's highlight the vector b, component b1, b2, b1, b2. This looks like a matrix vector product of the vector b, here with component b1 and b2 and something else, a matrix. And what components this matrix has? Well, it's going to have wrong color. It's going to have this factor here, and then this component in the component 1 1, and this number here in the component 1 2. So it's going to be something of the form 1 over delta multiplying all the components, and then we are going to have d and minus b, and then negative c and positive a. Okay, so negative c, positive a, as that is the matrix here. So we have found a matrix here. Let's call it matrix A tilde, and then our solution X can be written as this matrix A tilde acting on the vector B. So now the idea is to, what is A tilde? Let's write it down clearly here. A tilde is 1 over delta D minus B minus C A. And what was delta? Delta was AD minus BC. So this is our inverse matrix. So now what we say is that the conclusion here is therefore, or then, the matrix A inverse is that is 1 over delta D minus B minus C A, and well, that is the delta. So we obtain a formula for the inverse matrix. So maybe it's a good idea to check that this is actually the inverse matrix. So let's check. So that is the exercise, but let's check. What do we need to check? Well, if a matrix A has the form A, B, C, D, then A inverse is 1 over delta, and then we need to multiply by D in this position, A in that position, negative whatever B was, and negative whatever C was. Okay, let's check that this is the case. How do we check? We need to verify to compute or we need to verify. Let's say we need to verify that this matrix times A inverse is the identity, and on the other side too, this matrix times the original matrix A is the identity. So let's check that. So we don't need that anymore, and let's do this calculation. So for example, what is A? Let's do it on this side first. A inverse, so A, that matrix we found times A, what is that equal to? Well, we have 1 over delta, then we have here the coefficient D, the coefficient negative B, negative C, and the coefficient A, and we need to multiply that by the original matrix, which is AB CD. And we know what that is equal to. We still have the factor 1 delta outside, and this is okay, let's do it down here so we have a little bit more space. Let's put this a little bit closer so we can see it, and now we can move that law over here. And what is that equal to? Okay, this column times that row. So we are going to end up with AD minus BC. Then this column with this row, so we are going to end up with minus AC plus AC. Then this column with this row, so we are going to have BD minus BD. And finally, that column, this row, and we get minus BC plus AD. So, this is 0, this is 0, and we end up with 1 over delta. And notice, what do we have over here in the first component? Well, that is delta, then 0, 0, and delta again. So yeah, this is the identity matrix. So A inverse times A is the identity matrix, and there is an exercise now. Show that the other equation is also true. So that is the inverse matrix. So we can summarize what we have done in the following statement down here. First, we need to introduce a number that decides whether the matrix is invertible or not. It's called the determinant. The determinant of a 2 by 2 matrix A with coefficients A, B, C, D is a number that we call delta, but is also called det A, and is also denoted with straight bars. Matrices have brackets, and when you put straight bars, it's also not a matrix but a number, and is this number here. These are all names for the same quantity, and the quantity, so let's okay, here, and the quantity, this quantity here is the product of these two elements in the diagonal minus the product of the other two elements. That's the determinant. Now, when that number is different from 0, then we can compute the inverse of a matrix. So a matrix A with components A, B, C, D is invertible if and only if, so this is the same as saying in both directions the statement, if and only if. So this is we write it in this way, if and only if, with two F's, the determinant is different from 0, and in that case the formula for the inverse matrix is switch these two elements in the diagonal and change the sign on the other two and multiply everything by 1 over the determinant of a matrix. So that is the conclusion of the calculation we have done in the previous page. Let's see how we can use these formulas in a simple example. Suppose we have a matrix A and we need to find the inverse using the formulas above. So let's keep the formula there. So solution. First thing to compute the inverse of a matrix is to verify whether the matrix is invertible or not. So we need to compute the determinant. So the determinant of matrix A is going to be, well, the multiplication of these two coefficients minus these other two. So we get 4 minus 6 is negative 2. It's not important that it's negative. What is important is that it's different from 0. So then we can compute the inverse, and the inverse is going to be nothing more than 1 over the determinant. So 1 over, in this case, negative 2, 1 over negative 2. And then what do we need to do? Well, we need to switch the components 1 and 4. So 4 goes here, 1 goes there, and we need to change the sign on the other two, keeping them where they are, but just changing the sign. So let's, since these two coefficients are not divisible by 2, we keep the 1/2 outside, but the negative sign, we are going to put it inside, so we don't carry a negative sign outside. And an equivalent way of writing it is this inverse matrix is 1/2, and then we have negative 4, 2, 3, negative 1. Alright, and that's it. This is how we use the formula. So now would be maybe a good idea to verify that this is actually the inverse matrix. So how do we verify? Check or verify. Well, we need to do the calculation. Let's do the multiplication on the other side now. A inverse, as the one we did before. So what is that? Matrix A first, so 1, 3, and then 2, 4. Then we have the factor 1/2, and then we have this matrix that is negative 4, 2, 3, negative 1. Where do we put the 1/2? We can put it inside here, or we can put it here, or we can leave it outside. So we leave it outside. We'll see what we get. And now we do the matrix multiplication, which is -4 plus 6. Okay, that was this column, this row, and now this column, this row, and you see what we get. We get -12 plus 12. And now if we do this column with that row, then we are going to get 2 minus 2. And finally, the second column, second row, we are going to get 6 minus 4. And there it is. We get our matrix 1/2, and then we get 2, 0, 0, 2. That is what, this is exactly the calculation we did over here for determinant 2. Well, actually what we got is, because I changed the sign, is minus, 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 but it doesn't matter. So we get identity 1, 0, 0, 1, which is what we call the identity matrix. So we verify that this is the inverse matrix. We need to do the other product, but it's going to work. So now let's use this inverse matrix, the formula for the inverse matrix, to solve systems of differential equations, like this system here. Suppose you want to solve this system. Well, what we should do is, for example, compute x1 from this equation by moving this to the other side, and then put that in here and compute x2, and then go back and solve for x1. Or solution, or we can do something else. We can write the system in matrix form as 2, 2, 1, 3, that multiplies the vector variable x1, x2, and this is equal the vector 1, 2 on the other side. And now we have this matrix here that we would like to know whether it's invertible or not. So we compute the determinant. We don't have a name for the matrix, but this is not a problem, because our notation for determinant includes the case we don't have a name. So this here is actually the determinant, which is 6 minus 2, so is equal 4. And the nice thing of that is that it's different from 0. So now we can compute the inverse of that matrix. So if we call, now we are going to have to give it a name, 2, 2, 1, 3 is our matrix. Then the inverse matrix is going to be 1 over that determinant, and then what we need to do is we need to change the 3 with the 2, and then the sign in the -1 and in the -2. That is the inverse matrix. And with that, then we know that if we have our original system written as ax equal b, well, this is a vector and this is a vector, that implies x is a inverse b. So that is the formula for our solution. X is going to be nothing more than 1/4 3, -1, -2, 2, acting on the vector b, which is the vector 1, 2. Let's do this product. The 1/4 is still outside. The first column with the first row is going to give us 3 minus 4. The other is going to give us -1 plus 4. So we end up with 1/4, and then we have -1 and 3. So here is the solution. x1, the first component is -1/4. The second component is 3/4. And this is how we use matrices and the inverse of a matrix to find solutions to an algebraic system of equations, and we avoid the method of substitution, which is more complicated. Another example where we can use the inverse of a matrix and all we know about matrix algebra is to solve equations where the unknown is a matrix. For example, this equation here: find a matrix X such that this equation is satisfied where matrix A is this matrix B is that matrix, and C is that matrix. The first thing we should figure out is what is the size of this matrix. It's obvious that it's going to be 2 by 2, but let's double check that. Solution. So we have an equation that is matrix A acting multiplying matrix B multiplying matrix B, and all that has to be matrix C, and we know that this is 2 by 2, this is 2 by 2, and this is 2 by 2. So matrix X has to have the same number of rows as the number of columns. So here we need a 2 because these two have to be the same. These two with these two, and then it has to be also 2 because the number of columns on matrix B had to match the number of rows on matrix B. So it has to be 2 by 2. Alright, now that we know what is the size of matrix X, there is at least 2 ways to solve this problem. One is the old way. So the first way, one way is, well, write down all we have, which is matrix 1, 3, 2, 1. This is matrix A. Now we know that our matrix X has shape 2 by 2, so it's going to be x11, x12, x21, and x22. Then we have matrix B, which is 2, 1, 1, 2, and then all this has to be equal matrix C, which is 1, 2, 2, 1. One way to solve this problem is then do all these products. For example, let's do this product first. It's going to have a bunch of x1 and x2, so it's going to be a matrix 2 by 2. And then multiply that by 1, 3, 2, 1. Do these two products, and you're going to end up with one matrix 2 by 2 that is going to have a big coefficient here, 1, 1. Then it's going to have another big coefficient here, 1, 2. Coefficients 2, 1. Coefficients 2, 2. And that has to be equal the matrix 1, 2, 2, 1. And these coefficients are going to be long expressions here containing x11 all the way up to x22. All the 4 components of matrix X. And this equation is actually 4 equations. This coefficient has to be equal 1, this coefficient has to be equal 2, and so on. So we have 4 equations of the form some big coefficient here, 1, 1 equal 1, some another big coefficient here, big expression, 1, 2, that has to be equal to, then another expression which is the coefficient 2, 1 equal to, and the 2, 2 which is equal 1 in this case. So this can be written, this system can be written as a matrix acting on a variable vector, and our variable vector, recall, now is x11, x12, x21, and x22. all that acting. So, and here we have a big matrix that is 4 times 4, and that has to be equal 1, 2, 2, 1. So that's one way to do it, and here we have a big complicated expression of all the coefficients in this matrix. That's one way, but there is a simpler way to solve it. This is the old way. We have 4 unknowns, a big system, and we solve it. Another way. Well, let's write down our system. Our system is matrix A acting on matrix B acting on matrix B, X on B equals C. And we can start asking the question, is matrix A invertible? Well, that is easy to decide. We just compute the determinant of matrix A, and matrix A is the first matrix here, so the determinant is going to be 1 minus 6, so it's negative 5, which is different from 0, so yes, it's invertible. And what about matrix B? Is matrix B invertible? Well, we compute the determinant of matrix B, and the result matrix B, by the way, is this matrix here, so 4 minus 1, so it's 4 minus 1, so it's 3, so it's different from 0, so yes, they are invertible. So here is one thing we can do. If we have that case, matrix A invertible acting on X acting on matrix B, all that equal matrix C, we could very well multiply from the left the whole equation by the inverse of matrix A, because it exists, because the determinant is different from 0. And then on the right, we can multiply by B inverse. So you see, B inverse is multiplied from the right in the equation, and matrix A inverse is multiplied from the left. And if we do that, in these two factors we get actually the identity matrix, and here also we get the identity matrix. So we have a formula for matrix X, and matrix X is nothing more than A inverse multiplied by C multiplied by B inverse in that order. The multiplication has to be done on the right hand side in that order. So now the only thing we need to do is that product. But first, not the only thing to do. We need to compute the inverse matrix. So we know that matrix A is, what was that? Matrix A was 1, 3, 2, 1. 1, 3, 2, 1. So that implies that matrix, the inverse of A, is going to be 1 over the determinant. What was the determinant? We have it right here. It's negative 5. So negative 5. And then what do we need to do? We need to switch the diagonal elements. Nothing is going to happen there. They are the same diagonal elements. Then negative 2, negative 3. We change the signs. And this is, we can leave it like that, but I like to put the negative sign inside. So let's do it. We're going to have 1/5 only. And then the matrix is going to be minus 1, 3, 2, minus 1. Okay, that is our formula for the inverse of matrix A. What about matrix B? Well, B is this matrix 2, 1, 1, 2, 2, 1, 1, 2. We have computed the determinant already, So B inverse is 1 over that determinant, which is right here, is 3. So 1/3. And then we need to switch the diagonal elements. Nothing is going to happen. And -1, -1. And this is a good formula for the inverse of B. And what is going to be x? Well, x is going to be the product of 1/5. Then we have the matrix -1, 3, 2, -1. I'm just copying this matrix here. Is the inverse of A. Then comes matrix C. Matrix C is right here. 1, 2, 2, 1. 1, 2, 2, 1. And then the inverse of matrix B, it goes right here. 1/3, 2, -1, -1, 2. Okay. And that's it. Now we need to do the product. We have two scalars outside, this one and this one. We can put them together and we can write them as 1/15. And in which order we do this product? We can do this product first and then multiply by that matrix, or this product first and multiply by that matrix. It's the same. So let's put here -1, 3, 2, -1. And let's do this product here. Okay, so we are going to have 2 minus 2 in the first component, 4 minus 1, -1 plus 4, and -2 plus 2. That is that product, which is going to be simplified into, well, we still have this matrix here, 2, -1, and then here we get 0, 3, 3, 0 again. Alright, now the last product, we still keep the 1/15 outside, right here, or better, right there, and then we are going to do the product 0 times, so we are going to get the 9. Then, so you see what I'm doing. That times that is 9. That column times that is going to be -3, because we have a 0 on the other component. -3. And here we get -3 again. So -3. And on the other component we get 6. So all these coefficients have a factor 3 that we can pull out common factor and simplify, and at the end we end up with 1/5. Then we have 3, -1, -1, 2. And that is our matrix X. So that's how we can use a little bit of matrix algebra and the inverse formula for matrices 2 by 2 to solve equations where the unknown is actually a matrix. In the last part of this video, we are back to the determinant, and we are going to try to see how the determinant of 2 by 2 matrices is generalized to 3 by 3 matrices. Recall that the determinant of a 2 by 2 matrix is a number that determines whether the matrix is invertible or not. And what we want is we want to find a similar number, which we are going to call determinant of a matrix A, for a 3 by 3 matrices. That is, what we want to do is we want to find a number for 3 by 3 matrices that determine whether this matrix is invertible or not. And one way to find this number is to use the geometrical meaning of the number determinant for 2 by 2 matrices. We haven't discussed that, but actually the determinant, the number determinant of a 2 by 2 matrix has a geometrical meaning, and it's this. If you write a matrix A 2 by 2 in terms of its column vectors, these are vectors with two components, so they are vectors on the plane, and the determinant of that matrix is plus or minus, so the absolute value of that is the area of the parallelogram formed by these two vectors. That is, you have a matrix A that can be written in terms of column vectors. Grab these column vectors and draw them on the plane, and these vectors determine a parallelogram. The area of that parallelogram is plus or minus the determinant of A. So the absolute value of the determinant is the area. So that can be proven, and now we use that property to actually generalize the number determinant from 2 by 2 matrices to 3 by 3 matrices. And the idea is then, when we have a matrix that is 3 by 3, now we are going to have 3 columns. Each one is going to be a vector in space. Now these 3 vectors determine in space a parallelepiped. So the 3 vectors in space in R3 determines this 3-dimensional object, and this object has a volume. So the idea is to generalize the notion of determinant so that the determinant for 3 by 3 matrix is plus or minus the volume of the parallelepiped formed by the vectors A1, A2, and A3, the columns of matrix A. This can be done, and then what one obtains is a recursive formula, a formula that can be applied if we know the determinant of a 2 by 2 matrix. Formula. Then we can compute determinant of 3 by 3 matrices, and if we have a determinant of 3 by 3 matrices, we can compute the determinant of 4 by 4 matrices, and so on. So we can get a recursive formula that works also for n by n matrices. But we are going to see only the 3 by 3 case. And here is the formula one obtains. It's difficult to obtain that formula, so we are not going to do it here. We just show the final result. And the final result is this. The determinant of a 3 by 3 matrix is computed in terms of determinants of 2 by 2s, following this formula. And we are going to see how this formula works in an example. Suppose we want to find the determinant of this 3 by 3 matrix. How do we do it? Well, we have here the recipe. Let's see what we have to do. Okay, we have the matrix that is 1, 3, -1, and then 2, 1, 1, and then we have component 3, 2, 1. And we're going to, this is a 3 by 3 matrix, we're going to compute the determinant of that, which is, in our notation, we put bars, and that means determinant. And what do we need to do? According to the formula. According to the formula, we need to compute that coefficient here, and then multiply that by the determinant of that matrix. So the coefficient 1, 1 is this one. So we have 1 multiplied by the determinant of a 2 by 2 matrix. What is that 2 by 2 matrix? Let's look a little bit closer. Has component 2, 2, 2, 3, 3, 2, 2, and 3, 3. So this component, this component, this component, and that component. So essentially, the determinant of this little matrix here. A simple way to identify what matrix we need to work with here is, notice that we have we are multiplying that by A11, this coefficient. So this coefficient, so erase this column, erase this row, and what remains is exactly that the matrix that goes there. So here, erase, let's put it like this, erase that, and what remains is the matrix that we need to compute the determinant. 1, 1, 2, 1. Okay? Then what? Then is a negative sign, so it's always a negative sign. Oh, sorry. There. Negative sign. Then we get the component 1, 2 with this component, which in our case is 3. And then a determinant of a 2 by 2 matrix, which is what you obtain if you eliminate this column, eliminate this row, and look what we get. 2, 1, 2, 3, 2, 1, 2, 3, 3, 1, 3, 3, 3, 1, 3, 3. So what we need to do here is we are focusing on this coefficient, we eliminate that row, we eliminate that column, and what remains is what goes here. 1, 1, 2, 1, 3, 1. Okay? And now is a plus sign, so it's a plus. So you see the signs are alternating. Let's make it a little bit bigger. It's a plus, it's a minus, and it's a plus. Alternating signs. Then comes the coefficient 1, 3, which is this one here, which has its own sign. Okay, negative 1, and then a determinant of a 2 by 2 matrix, which is, if we eliminate this column and that row, what remains is exactly what we have here. 2, 1, 2, 2, 3, 1, 3, 2. So back in our example, this is the coefficient we are dealing with, so we eliminate that column, that row, and what remains is what goes here. 2, 1, 3, 2. There. That is the recursive formula. It's not difficult, and now it's just a matter of computing the 2 by 2 determinants. So we still have the 1, we are not going to write it. And now what we need to do is we need to multiply these two coefficients minus these two, these two coefficients minus these two, and these two coefficients there minus these two, and multiply by the corresponding number. So it's 1 multiplied by 1 minus 2, and then minus 3 multiplied by 2 minus 3, and then minus, there is a minus 1 there, multiplied by 4 minus 3. Okay, so it's just negative 1. Then we have plus 3 multiplied by 1 minus 1. Okay, so this is 1. In this case is 1. So that is how you use the recursive formula to compute determinants of 3 by 3 matrices. And again, we are going to need this formula in a later video, and with that we finish our review on matrix algebra. See you guys in the next video.